All right, hey everybody. In this video, what I'm going to be doing is implementing the MinMax algorithm recursively. So far what we did was we have the MinMax algorithm, but we only have it, iterating 2 times. You can kind of see the pattern that's emerging from it. I also want to start this video with a couple bug fixes. So there's a few bugs in my code at the end of the last video, and I did some debugging and came up with a few solutions to them, and I wanted to share those with you. So first and foremost, I added in this here, um, which is very similar to what we had right here. But I added this after the AI makes a move. So if the AI makes a move and the game is in stalemate or checkmate, then there are no opponent moves. So we don't really need to go through all this and like score the board because like there's not gonna be any moves. So we want to make sure that we have the stalemate or checkmate values here. And because it's our opponent that's moving, then like negative checkmate is their best score that they can get. That is their max score if they're being checkmated. Otherwise, then we go through the moves here. So basically, I added in this, and I indented all of this code here. The next change that I found was starting out with inside of here. I think I had turn multiplier times checkmate, but now we're looking at our opponent's moves. So if our opponent makes a move and then the game results in checkmate, then that is their max score. They are putting us in checkmate. So this is bad for us. We still need the negative turn multiplier here. That is required. And then I think the other thing I added in is this piece here. This may seem really inefficient, and it is. And when you add this line of code in, game state valid moves, it's going to make your code a lot slower. And this is because for every opponent that your opponent makes, it's going to generate all of your possible moves from that position. But because our engine requires us to call this before checkmate is called, or checkmate is updated after the valid moves are found. That's the way our engine works. So when we make a move, we do have to generate the valid moves to see if there is a checkmate. So this will add some inefficiencies here, but there's sort of no way around it in order for us to checkmate. We'd have to basically think of a different way to do this without generating all the moves, and there's not really a good way of doing it, as we've talked about in previous videos. But everything else is pretty much the same. So the other thing I had to add in is because once we make a move that puts us in checkmate, and then we undo the move, we call undo move here, we call undo move here. These should reverse any checkmate or stalemate that happen. So in our engine, this is actually something we forgot to do. You're going to have to add these 2 lines of code into the undo move function. So at the bottom of the undo move function, I'm just adding in checkmate and stalemate to false. Basically, any time we undo a move, we can't possibly be in checkmate or stalemate. So we can just set those variables to false. So make sure you add those in. Otherwise, you'll run into some bugs. Okay. And then in our main, I think everything's pretty much the same. I think the only thing I added here was to be able to reset, have to set game over to false. So when you undo a move, in case a move was made and checkmate was found, then the game is over. That happens down here. Game over gets set to true and the text is drawn. And then it iterates to the next frame. So if we undo a move, we need to undo this potential game over is true. And so again, we're just going to switch those flags back off. Even if game over is already false, then this doesn't do anything. And same thing for resetting the board. So if you do this, if you don't have this, you'll realize that after the game finishes, you can reset and nothing happens. So that's a little bug fix. Didn't look into the king castling knight side through the knight on the queen side yet, but I'm sure I'll find that bug later and get it. It's on my to-do list. I just haven't felt like going back to that code yet. I'm sure some of you already found the bug that's causing it. So if you do, you could like post that in the comment section or something. You could post what was causing the issue, but or it might already be in the comment section for one of the castling videos. I'm not sure, but at some point I'll get to that. Okay, so I want to look. So basically, this best move method, it's okay. It's only looking 2 moves ahead, and we could certainly like iterate through these moves and find our best move, and then go through our opponent's moves and find our best moves. But this tree is going to just get exponentially bigger, and we're going to get to the point where we need to wait like 15 minutes for the computer to evaluate all these possibilities. And then if we go one depth deeper, it's going to take like 2 days. So this is unfeasible. And this is where we need to implement some more efficient algorithms into our code. So that's what we're going to be looking at today. So the first thing I'm going to do is I'm going to do something called a min-max algorithm. And this is sort of what we're doing with this for loop, trying to minimize our opponent's score. The min-max algorithm does this recursively. So it's not necessarily any more efficient, but it's a lot cleaner to look at. This code is, if you can imagine, if we went another layer deeper, it's just going to get very long, and it's going to be hard to debug. It's going to be hard to see where, if we were to make a mistake, where that mistake might be. So I'm going to go ahead and leave this find best move as is and create a new method underneath it. So we're going to kind of take a lot of the ideas from this method, but we're going to implement it recursively. Okay, so let's define a method, and we'll call this find move min-max. And this move min-max will still take in the starting state, our moves that we have already grabbed. Then we'll need to add in a couple parameters. So the first one, if you're familiar with the idea of recursion, then you'll know that there's something called depth in recursive algorithms. This is basically how deep you want to go before you shut it down. So this depth will represent basically how many moves ahead we want to look. So how deep into the game tree do I want to go before I come back up and return a solution? Obviously, like if I had infinite computing power, then I could just make this depth infinite, and it would just search every possible game of chess, and it would come up with the best move from every single possible game. Now, that's just impossible because there's so many games. At each branch, we're going to have it transposed to a different type of board. So we're going to realistically just put this depth at like 2 or 3 to begin, until we make our algorithm a little bit more efficient. And so we're just making this a variable for now. And then the other thing we need with the move min-max, when you're doing a move min-max, we need to pass in basically a Boolean variable that says which player's turn it is. And this variable can be true if it's player 1's turn, or false if it's player 2's turn. So I'm just going to call it white to move, as it will be a Boolean variable representing whether it's white's turn to move or black's turn to move. Now, in our last algorithm we looked at, we kept the best player move here. In this algorithm, it's a little bit different because we're going to be calling multiple iterations of this method. We're going to be calling this method recursively. So we need a global variable to represent the next move, because not all of our code is going to be in one iteration of this. So I'm going to use Python's global variables here to create this variable next move. And this next move, so basically we're going to need a helper method to call this. So I'm going to, instead of having find best move here, I'm going to create like a little helper method to call this for the first time. So this will be find best move MinMax. And this will be the method that we call. So it'll have game state and valid moves as parameters, just like this one had. So this will be the method that we call, and this will be the method that returns our global variable next move. All right, this is a helper method. Because it's going to basically, its only responsibility is to call the initial recursive call to this value and then return basically the results at the end. So we can now adapt our main from smart move finder find best move to find best move min max. So now we're implementing our new algorithm. So we're no longer using this method at all. This one just kind of, we're going to use it to guide us in terms of creating this next method, but it won't be called at all. Okay, so this helper method is going to take care of this. So this is a helper method to make the first recursive call. Okay, now what does our first recursive call look like? So find move min max, we still have to pass in our usual 2 parameters, but now our depth, this is basically going to be like how much we want to search into the tree. So I'm gonna make a global variable for this. We'll start at 2. It's going to be slow initially. So we'll go depth here, depth. That variable I just made sets to 2. And then whether it's white's turn to move. So this should be a true or false value. And so we can just really pass in the value white to move here. And so this will pass in either true or false. So now if white is playing the eye, this is true. If black is playing the eye, then this is false. And this tells our min-max algorithm basically where to start. Okay. And we'll just reset next move to none before we call this method. And that way, if it doesn't find a method, it's not set, then it'll pick its random move from here. So if that move that's returned is none, just keep track of it there. Okay, so the next part of this is it's going to feel very similar to what we already have done, but we're going to just adapt it a little bit recursively. So the main part of this min-max algorithm is if we reach a depth of 0 or we reach a state of the board that is at a that's at a stalemate or a checkmate, then that's like a terminal node. That's what it's referred to as. And at that point, we return the score of said board. Okay, so trying to think here. Yeah, we're gonna have this idea here of scoring it based on there. So how do I know if it's a terminal node? I check to see if depth is 0. That's the basic idea, because that means I start depth at like 4, and then each time I call the method, I lower this by 1 until I get to 0. 0 means, okay, I'm at the deepest that I want to go, and now I want to return up, and I want to evaluate the board right now at this position and see where I'm at. What's my best score, or what's my opponent's worst score? Best worst score, if that makes sense. So here, all we do is we just evaluate the board, so we can score the material of this and pass in game state board. And I want to make a change right now to the way we're scoring to simplify our code a little bit. So instead of scoring it purely based on material, which is like a really naive solution, what I want to do is I want to score it. So I'm gonna like create a method scoreboard, which is gonna be just like a little bit more instructive. So it's in this case, it's gonna take the game state entirely of the engine, and this will allow us to do things later on. Like, so an idea I have is when we generate the moves, as we're generating the moves, we can keep track of like basically how many valid moves each piece can make, or how many threats each piece is making. In other words, how many enemy pieces is each piece attacking? How many allied pieces is a piece protecting, right? So like a pawn protecting a piece is a better pawn than a pawn that's not protecting anything. A bishop or a queen that's attacking, 2 or 3 different pieces is better than a bishop that's just maybe behind the lines, just protecting 1 or 2 pieces, right? So we can add in stuff to our engine, and I'll do this in a later video, but I want to think about implementing my code in a way that it's ready for that. Once I implement it there, it'll be ready to plug in to this method here. So that's why I'm gonna move away from this score material. We're still gonna follow this similar algorithm. I'm actually gonna copy and paste this in, because this is still what we're gonna start with initially. But it's gonna have a couple other things as well. Okay, so first off, it's gonna take game state. It's gonna take valid moves. I'm actually, it's not using valid moves yet. So another idea I had for making a board position, evaluating a board position, is like the more moves you have, typically the better the position is. Not always, but that could be a factor because it gives you more options. It's a more complicated position if you have more possible moves. So it could potentially be better in that way. And this also means like your pieces are more active if you have more moves. So potentially we could look at like the length of valid moves and add that into our score somehow. But basically I want to pass in game state here instead of just the board itself, because I want to be able to check for the checkmate and stalemates inside of this method instead of outside. Okay. So I'm going to pass in the game state here, and we're still going to start with our score there, but I'm going to add in a little bit of, and then this I'll have to switch to game state.board. But I'm going to add in a couple lines of code here to check for checkmate and stalemate. So if it is checkmate, now I want to score the board so that if it's white's turn and it's checkmate, it returns a very bad score. So if it's white to move, and let me put in comments here just to help with any confusion that might be happening right now. A positive score from this is good for white. That means white's winning. A negative score is good for black, means black's winning. So if we have a checkmate and it's white's turn to move, that's bad for white. That means white doesn't have any moves, and therefore black is the winner. So we should return a negative checkmate. Black wins. Otherwise, we should return positive checkmate, because that means white wins. All right. And we should do that before even trying to score the board. There's no point in looking at and counting up all the material if there's a checkmate on the board. So before I go through this board and score it like I did before, then there's no point in that. So we just skip it with this return statements. All right. The other thing we need to look at is if it's stalemate. So if it's stalemate, then we should just return stalemate, which is 0. neither side wins. Okay, so this just will this will just make it a little bit easier to work with now, because we don't have to worry about checking for checkmates and stalemates inside of our min-max algorithm. So that's why I wanted to do this. So here, if depth is 0, then we can just return the score material, and then when we return later and we return a score, the first thing it checks is this here. So yeah, if we could also do terminal nodes here, so to make it a little bit more efficient, because this will only score the board if depth is 0. Does that actually make it more efficient? Let me think here for a second. I'm trying to think if we should check for checkmate and stalemates here. I guess it doesn't really matter. If there's no valid moves left, we're going to see that it gets returned pretty quick here. So, all right, we won't do that. So let's just move from here. And the way the min-max algorithm works is there's basically one if statement for player A and one if statement for player B, and we score one, we try to maximize, the other we try to minimize. Black's always trying to minimize their score, white's always trying to maximize their score based on a board. So we'll make a we'll see whether it's white's turn to move, if this is true or false, and this is going to basically be the main part of our algorithm. This will tell us which way we should kind of start. Are we trying to maximize or are we trying to minimize? So if it's white's turn to move, we're trying to maximize. So the way this will work, our max score, we're going to start at a very negative score. So we could start at negative checkmate. Basically, that's the worst score possible. Then we'll go through our moves just like we did before. So we'll make a move. And you'll notice that this code follows very similar to what we already did. After we make the move, we're going to go ahead and score our board. So our score, let's call scoreboard here, pass in the game state. Sorry. We don't call a score. That's what we used to do. Now what we do is we call recursively the function. We pass in the game state. We pass in the next set of moves, which I haven't actually grabbed yet. So let's go ahead and grab the next moves. So what are the next moves now? Well, let's get valid moves. So we'll pass in the next possible moves, the new game state after we make that move. We'll pass in depth -1, and then we'll pass in not white to move, basically negating this. So if it was white's to move, now it's false. You could also, since we know that white to move is true, we could also just put in false. I think it's slightly more efficient. It doesn't have to do one little Boolean operation. I don't know that you would actually be able to notice if that made a difference or not, but every little efficiency will help. So let's do that. And so what this will do is this will now go into the next layer deep. So if I start with depth of 2, now depth is 1, and I'm going to be going into this part of the statement. So let's look at that now. So this is if it's not white to move, now I want to minimize the score. So my minimum score, start at a very large value and then try and minimize it. So we're going to start with the minimum possible value, which is checkmate. And we're going to go through the moves. Again, these moves are the ones that are being passed in. So right now, it's going to be the next moves that were generated here. Based on this recursive call, it's going to come back into here. Depth is not equal to 0, so it's going to go into the else statement. Same thing, we make the move. We generate the next moves. And then we find the score by calling this move min-max function the same way we did before, but now we kind of pass it back to the maximize part of the function. So we pass it back with a true. All right. Eventually, what's going to happen is we're going to return a score within this if or within this else. So this will now call back, and eventually we'll get to depth is 0. It'll score the current board, and it'll pass that back into either one of these functions, whichever one we were in, white or black, to move. So now I want to maximize this score. So in my white to move, I'm going to say if score is greater than my max score, then I'm going to set my max score equal to score. So that becomes my new max. And if I'm at my uppermost depth, if I'm at my max depth, remember max depth is 2, that means that I'm actually at the top call. I'm at the first call of the method, which is the actual set of the first set of moves. So like we're going a couple layers deep. I don't want to return a move. I don't want to set a move that's like not a move that I can currently make, right? I want the best move of the ones that I can currently make, but I'm making a whole bunch of moves, generating a whole bunch of moves down the line and finding the best score at that point in time. Then when I come back up the levels, that's where I want to set the max move. So here, if depth is max depth, then next move equals move. And what did I call it? I didn't call it max depth. I just called it depth. Sorry. So this variable here, depth is 2. So basically, if my depth is 2, then that means I've searched all the possibilities below it of that tree, and I've found the best score at that point in time for that particular branch, and that now becomes my next move. And if I find a better score in another branch, then that becomes my best move. Okay. Now let's see. Okay, so we still need to make sure we undo the move. And this will undo the checkmates that we had, all that good stuff. And then after we look through all the moves, we should return max score. So this will cause the recursion to percolate back up. When you are using recursion, you always have to make sure that you have return statements in all of your branches, which we do here. All right. And so I'm going to basically add a similar thing, but now it's minimizing. So if score is less than min score equals score. And then if depth is depth, next move equals move, same exact logic. Undo move, and then return min score. All right. And thus, this is our min-max algorithm. This is where that name comes from. So this code, if you compare this code to this code here, it's actually doing the same exact thing. Making a move, getting our opponent's move, scoring that board, finding the max, finding the min, finding the max, finding the min. But this one only can go into depth 2, and then we'd have to add more to go like another layer deep. And so this method would continue getting it longer and longer. This method, because we're doing it recursively, all we have to do is change this variable depth. If I go depth 3, now my algorithm's looking 3 moves ahead. Now it's only looking 2 moves ahead. Now it's just looking 1 move ahead. Now it's 4 moves ahead. So we have some control over how much we want our computer to think at these various points. Okay. So this is what's called a MinMax algorithm. Now, I think let's go ahead and test it out and see if we get any errors, and then I think we'll probably wrap up this video here. But let's give it a shot. All right, we got a couple errors here. Oh, I forgot to add in make move. Forgot to tell it which move to make. That would be helpful. Probably forgot that down here as well. All right, and you can see it's thinking a little bit. That's why it hasn't. I have both my AI set to being false. So player 1 and player 2 are both false, which is why it's taking a while to think right now. And my depth is set to 3. So you can already see when I went to depth 3, it's taking quite a little while to come up with a move. Okay, finally it made a move, and we can see it decided to move the pawn 1. So one of the things you're going to see is 1, it's really slow, and 2, it's not actually making that smart of moves. And it's a combination of factors. One is the fact that we haven't actually made this algorithm more efficient. We're still checking every possible board state. So that's just going to be highly inefficient. The second part is that we're not actually scoring the board in a very efficient way. We're just adding material. So that means a lot of moves look the same. We haven't added any positional values to our scoring algorithm. So we're going to do 2 things in the future videos. So the next thing we're going to do, we're going to make this algorithm, one, because you can see the repeated code, we're going to combine this into like one for loop, and I'll show you how to do that. And then we're going to add in, which is called, I think it's called Negamax is the algorithm. And then we're going to do Negamax with alpha beta pruning, and I'll explain what that is. But that's kind of, we'll add some efficiencies to it. Finally, then we'll look at scoring the board more efficiently and trying to come up with algorithms that think a little bit more. So we'll look at pawn advances. We'll look at like positional play. We'll look at threats. We'll look at attacks. So we'll look at kind of like what makes a piece good versus what makes a piece bad, and we'll try and balance all those things together so that our computer starts to make more intelligent moves. All right. I'm gonna wrap it up from there, though. I hope you guys enjoyed this this video on the MinMax. If you're a little confused about the algorithm, Wikipedia has a great page with some good tree diagrams of MinMax and the pseudocode for it, so you can read through that. I think it's a pretty good resource. But yeah, until next time, I'll see you.